Let's look at the example 1 again. We've already worked out this problem using the analytical method and the finite element formulation. But we did this all on paper by using the methods that were introduced to you in the formulation and also an analytical method that you already knew from your bachelor's. Now, this is a very simple example, and yet I'm going to follow all the steps that I follow when I carry out a finite element analysis, no matter how big or small that problem may be. The first thing that I must do before I set up a finite element problem in a finite element software is to understand the problem and try to make out as much as possible from this problem. So, of course, for me, the first step is always plan. First, I look at the problem and I see what do I know and what do I need to know from this problem. I know that there is a uniform varying cross section bar. That means it's only going to deform in one direction, which is in direction x. It has a load P acting on it, which is also in the direction x. It has certain geometric properties which are known to me. So I have W1, W2, L, and the thickness of the bar in the out of plane direction. I also know the value of the load which needs to be applied on it. I know the material properties which are defined by the Young's modulus and the Poisson ratio. What is not known to me and what I must find out is the axial displacement at various locations in this bar, as I have done with the analytical and with the other finite element formulation problems. What is extremely important is to know, are there any boundary conditions? As you may be able to guess, if there are no boundary conditions, then the problem can never be in equilibrium. Luckily and fortunately, I have a boundary condition in this problem, and that is that the left edge of this bar is fixed. So if I divide this bar into number of elements or into even one element, I know that one of the nodes is going to have a displacement which is given as 0. So now I have put everything into perspective. I know what I want to find out from the problem. I have no data that's missing. That's a good sign. So now I can go to the next step. The next step is predict. I want to first predict or guess what's going to happen when I carry out this analysis. This is a really simple problem. So I know that the bar is actually going to stretch in a certain way, maybe something like this. That was not a very good drawing, but yeah, you get the drift of what I mean. So it's going to stretch in that direction, and there will only be axial direction, so it's only going to move in x, and everything else will come out to be 0. So I've made a very good prediction. I know exactly what to expect. Sometimes you will not know what to expect, but you have to make some assumptions. You have to come close to it. So you make some idealization and you say, yeah, this problem looks somewhat like another problem, and in that problem there is a behavior of a beam or something like that, and then you can predict somewhat what you're looking for, because this is extremely important for verification, to make sure that what you see is actually what you expected to see from your problem. If I apply a pulling force, then the result should be pulling, not pushing. And these are small verification steps that you will learn to carry out during this course while we are doing many kinds of tutorials. So now I've planned everything. I sort of know what's going to happen. So I'm now going to start with the pre-processing. The idea of pre-processing was first to plan the discretization. Now in this problem, I'm going to do it in two ways, just so that I can teach you, but you don't have to do it in the same way. I'm going to discretize it into two kinds of problems. First, I'm going to discretize it such that this problem is composed of only one element, and then I will do another one where it is composed of 4 elements. The differences are quite simple. If I divide this region into one element, then I will have only one bar element. It will have 2 degrees of freedom, u1 and u2, at the two nodes 1 and 2. I know from this that u1 is 0, and I only can find out the value of u2. That's not a problem if the question was to find out what is the edge axial displacement. However, my problem here is that it has asked me to find out the displacement at all these different locations. So although this is a correct discretization because it's just a bar element, it's a linear bar element, and if I will divide it whether into one element or four elements, I will get the same results. Now, the only thing is I can't extract the results because it's not calculated across the element, but it's calculated only at the node. So I'll have to do some extra post processing. To save that effort, I can then easily divide it into four elements. And in that case, I will have 1, 2, 3, and 4 elements. And I will have 5 nodes. So I will be able to find out the 4 unknown displacements at different locations in X. That's the only difference. But I would like to work this out so you get an idea of how it is done and what makes a difference when I want to find out more than one result. You can also see if there will be actually an error. So this is a good exercise. Let's find out what is the error between U2 from element 1 problem and U5 from element 4 problem. So what would be the error between them? So this is how we've discretized it. Now that's not enough. We also need to put in other things into the model. Now if I have only one element, I need to know when I describe the element, I have to describe the behavior, right? So let's go back to element behavior. Now under element behavior, I will be requiring certain properties. So I will be requiring the Young's modulus that I have because it is going to be given as K is equal to EA by L, which would be the stiffness. I already know the length of the element, whether it's one element or many, because that's given to me. The Young's modulus is also given to me. The area can be calculated by using the equation that we did for the analytical problem as well. So this is how we calculated the area. Now this will work easily when you have one element. It will also work quite easily when you have multiple elements. However, there may be slight differences. So there are different ways of discretizing this problem. In this case, when you are using this equation, what you are doing is that you are literally dividing your problem into 4 pieces like this. So you will get the varying cross-sectional area. So the area is going to be calculated at this location. Okay. Now, what you can also do, this is an alternative method, is that you can use equivalent rectangular areas. And that's going to give you a slightly different result. You can try this as an alternative to see what are the differences, maybe with your neighbor. So one person does this, the other one. Of course, if you're an online student, then you can try both on your own, or you can also check with discussion board, ask someone if they did the other method, what kind of result did they get. But for this current analysis, I'm only going to use the equation. And for that, it's quite easy for me to check the area because I already calculated it before. So I have the value of the area of cross section, and that is given as, I can write it here so that we don't forget. So I have, in case of one element, it's quite easy. But in case of 4 elements, I will have A1 is 136.72, A2 is given as 117.19, A3 is given as 97.66, and A4 is given as 78.125. Don't worry, all these values are also provided in the reader. So you can simply copy it out if you are too lazy to calculate it yourself. Although I expect you to have calculated this already while working out the problems before. So let's go back to Abacus now and put in all these properties and set up this element behavior. And if we need to come back and think about something else, we can already look at this sketchboard once again to plan our problem.